In this video, we're going to start talking about confidence intervals, which is the topic in Chapter 7 of our textbook. Remember that if you need to see any additional examples about any of these topics, then you're welcome to try finding that course textbook that's mentioned in the syllabus. It should be available as a PDF online if you just Google it. So I'd recommend doing that now that we don't have these face-to-face contacts. But I think maybe a good starting point for confidence intervals would be to go back and review the stuff that we talked about in Chapter 6 so that I can sort of motivate what Chapter 7 is doing. So remember in Chapter 6, what we were trying to do is we were trying to estimate a population mean, which we denoted by mu, using a bunch of sample means, and those sample means we denoted by x bar. And remember, what we saw in Chapter 6 was that as long as your sample size, n, is bigger than or equal to 30, then if you send a bunch of teams out to compute these x bar values, so they go out, they survey 30 people, they compute their sample means, what we saw is that these sample means will be normally distributed, so they'll have this bell curve distribution. And the average of all of those sample means will be mu, and the standard deviation of the sample means will be the population standard deviation divided by the square root of n, where n is the sample size. And that's what's summarized in this little box over here. So that's what we talked about in Chapter 6. So in Chapter 7, what we're trying to do is we're trying to use this strategy of computing these sample means to estimate the actual mean or the population mean. But this time, rather than just coming up with a single estimate like x bar, instead what we want to do is we want to come up with a range of estimates and say that we are, let's say, 90% confident that the actual population mean falls within that range. So maybe let me make up another drawing down here. So let's say that we're in the same situation. We're trying to estimate this population mean, but all that we can do is we can send out some teams to survey some large groups of people and compute x bar, their sample means. So remember that here, the distribution that we would expect our teams to come back with is a mean of mu and a standard deviation of sigma over square root of n, where sigma is the population standard deviation. So this is what we expect our team's data to be distributed like. So now let's say that what I want to do is come up with a range of values so that I'm about 90% sure that we've captured the actual population mean within that range. So maybe let me draw a little window here. Let's say that 90% of this area, the area under the curve, is contained between those two bars. So this would represent what I'll call a 90% confidence interval. But notice that 90% of the time, my team is going to come back with an x bar value that is pretty close to the mean mu. In particular, it's going to be within this distance, the distance from the middle to this vertical bar over here. So maybe let me call that distance E for error. So that will be the margin of error in this study. And what I'm saying is that 90% of the time, so maybe I'll write this, 90% of the time, mu is between x bar plus or minus that margin of error. So in other words, our teams can come back with a bunch of different x bar values, but 90% of the x bar values that they get are going to live somewhere between these two vertical bars. And those vertical bars are going to be close enough together so that if I just take the sample mean that my team brought back and either add or subtract that error, I will have the actual population mean inside of that range. Okay, so let's think about what this error would be in this particular picture. So what I said earlier is that I wanted 90% of the area to live on the inside. And what that means is that 10% of the error lives on the outside. And usually we're going to write alpha for the error that lives on the outside, the area that lives on the outside. So in this case, alpha would be 10%, which we'll usually write as a decimal, which is 0.1. But if 10% of the area lives on the outside of these vertical bars, that means that 5% of the area lives over here. So alpha over 2 would be 0.05. That'll be the area on this side and also the area on the left. So alpha over 2 would also be the area over here on the left side. Okay. So what we can do is we can think about the z-scores that we talked about last week. Now, let's say that I want an area of 0.05, like we had in this upper picture, to live on the right side over here of a particular z-score. What I can do is I can look up the z-score that has an area of 0.95 over here on the left, because remember that our table of z-scores has all of the left areas. So if I want a 5% area on the right side, that means I want a 95% area on the left side. And if I look up a 0.95 in the table, what I'll end up getting is a z-score of about 1.645, something like that. And that's the z-value for this particular range. That's how far or how many standard deviations we have to be away from the mean in order to land over here. But remember that the z-distribution has a standard deviation of 1. So if we wanted to convert this to an actual error estimate in terms of the original picture that we have up here, I need to take this distance, which was a z of 1.645, and I need to multiply it by the actual standard deviation that we had up in this picture, which was sigma over the square root of n. So if we put all of that together, what that says is that the error that I wrote down earlier is going to be 1.645, which is the z-score, but I need to de-standardize it so that it lives on the picture that I started with originally, the x-bar picture. So that would be the z-score that I found times sigma over the square root of n. So that's the error that we're going to work with in that upper picture. Or sorry, that's the, I can't remember if I said area or error, but this is the error. Sometimes it's called the margin of error. And this 1.645 in our notes, we're usually going to just denote as z of alpha over 2. What I mean by that is that's the z-score that has alpha over 2 as its right area, just like we had up here. So I could write this as z of alpha over 2 times the standard deviation in our original picture. And that gives me this error distance that we're willing to put up with. Okay, so that's a very fast summary of what we're going to do in section 7.1. What I'd like to do is I'd like for you to just keep these pictures in mind, and then we'll start the notes. If that was too fast for you, that's totally fine. I think you'll catch on as we go through some of these examples. But what I'd recommend is going through some of these examples with me, and then if you need to rewind the video or start it over to go through these pictures again at the end, then you're welcome to. So let's get started on the actual notes here. I just wanted you to have some pictures to accompany it. So in this section of notes, we're talking about confidence intervals. There are two kinds of estimators that we've talked about so far. One is a point estimator, and those are the things that look like this. So things like X bar or S, these are things that we can compute about a sample, and we can use that sample information to try to guess the value of a population's parameter. So we've been doing that recently with X bar. We've been taking some sample mean, and we've been trying to use it to estimate a population mean. And now what we're going to do is we're going to look at the second kind of estimator, which is the interval estimator. So now we're going to try to come up with an interval, and inside of that interval, we can be reasonably confident that the actual population parameter lives inside of that interval. So here I'm going to introduce some terminology. We have this confidence interval, that's the range of values that we're going to use to try estimating our population parameter, and we also have a certain degree of confidence. So remember, in the picture that we talked about a second ago, in the picture over here, I wanted a 90% degree of confidence, and that meant that 1 minus alpha was 90%. That's the area that lives on the inside of this graph. And the area on the outside then was 10%. And if we want 10% of the area to live on the outside of these walls, that means that 5% lives over here to the right and 5% lives over here to the left. Okay, so this is the example that we just talked through. The degree of confidence that we just used was 1 minus alpha was 90%. That means that alpha, the area on the outside of our bounds, was 10%. And as we saw earlier, that means that the z-score that we would need to go to the left or to the right by is 1.645. Okay, and we'll see that in a table in a second. But I just want to point out that these degree of confidences and their corresponding z-scores, they're listed in this nice convenient table. So you don't always have to be using the z-score table, but I'll show you how to do that in a second. I do want to mention that in this set of notes, all of the formulas that we'll need for this entire chapter are listed on these front 2 pages. So we have this first page that has a bunch of formulas, and then the second page that has a bunch of formulas. I think that for now it would be best to just ignore most of the formulas. We'll go through them bit by bit as we go through these different videos. But for now, what I'd like for you to do is just pay attention to this formula, which is the one that we're going to use right now. This is how to find the confidence interval for estimating a population mean. And notice that this is the same thing as x bar plus or minus the error that we found a second ago. The left side is x bar minus that error that we found a second ago. The right side is x bar plus the error. And we can be reasonably confident that mu, the actual population mean, lives between x plus or minus the error. So I'll show you how to apply this formula in a second, but I just wanted to point out that this is the stuff that we talked about with the pictures a second ago. So that's one formula that we're going to use in this first section, and then the second formula that we're going to use is this formula. This formula actually follows from what we had a second ago, so notice that a moment ago I had that the error that we were willing to put up with was the z-score that you get from alpha over 2. Remember, alpha over 2 is the right area in this particular example. And then times a sigma over the square root of n. If you rearrange this equation to solve for n, what you get is this equation. So this is the second formula that we're going to be using, but it basically follows from the first formula. This is just another way of rewriting the error. In this case, you could use the formula to decide what your sample size should be given a certain amount of confidence and a certain error that you're willing to put up with. So we'll talk about how to apply that formula in a bit. But those are the first 2 formulas that I want to use on the first set of examples. So that's the general setup for this section of notes. I think what I'll do is I will cut the first video here so that we just have an overall description of what this setup is going to be, and then we'll go through in our next video all of these examples.